Hello everyone, this is Lecture 10 of ComSci 141, Parse Trees. Previously, we discussed context-free languages, context-free grammars, how to do leftmost and rightmost derivations, how to simplify the CFG, and how to convert them into Chomsky normal form. So we are now in our second topic, which is parse trees, and in today's video, we will discuss what parse trees are, some parsing algorithms, and how to handle ambiguities in grammars. So let's start with parse trees. Before that, let us review some terminologies about the trees. Remember that trees are a special type of graph wherein you don't have cycles, so it's acyclic, and you have parent-child relationship uh, among nodes. Okay, so in trees, you have something called the root, which is the topmost node. So in this case, that would be F. Okay, and then you have leaves or nodes without children, and that would be A, C, E, and H in this tree. Then you have interior nodes, or the opposite of leaves, so those with children. So the interior nodes in this tree would be F, B, D, G, and I. Then of course you have the parent and the children nodes. So the parent of C, for example, is D, the parent of D is B, the parent of B is F, and so on. And then the children would be those that are below. Okay, so the children of D, for example, would be C and E. The children of F would be B and G, and so on. Okay, so you remember your tree terminology from um, maybe your 142 or your 123 subjects. Okay, so now let's define parse trees. Parse trees are trees that are labeled by terminals and variables of a context-free grammar. So remember that in our context-free grammar, we have variables which represent languages and terminals or your the terminal strings, right? So a parse tree is just a tree wherein inside your nodes, the labels are either terminals and variables. And the parse trees show how the string is derived from a context-free grammar. So it shows the derivation. And later on, we will see that it is important in showing ambiguity in the grammar. Okay, so this is an example of a parse tree. So given this context-free grammar for balanced parenthesis, so you start with S, which is the start symbol, and then you can derive from S, you can have SS, like this one, and then this S could be replaced with parenthesis S parenthesis, so we have this one, and then this S could be replaced by open close parenthesis, and then the same with this one. So this is the overall parse tree, and we call the string that is derived by the parse tree the yield of the parse tree. So in this one, the yield would be um, open, open, sorry. Uh, so that would be open, open, close, close, open, close. So that would be the yield here. Okay, so that's the yield of your parse tree. So as we said, the yield is the concatenation of the leaf labels from left to right, and that is the derived string of the parse tree. Okay, so for the parse tree, you start with the start symbol at the root, and then the children nodes are one of the parent nodes productions. So going back here, you'll notice that the children, for example, of S would be SS, which is one of the productions here. And then for S here, it's replaced with the open close, which is one of the productions of S again. Okay, and then the interior nodes are always variables. Okay, so if it's a variable, you always replace it with another production. Okay, so that the leaves should only be terminals or epsilon. Okay, so that's it. So remember that interior nodes or those with children has to be variables, and only terminals or epsilon can be at the leaves. You cannot leave variables as a leaf. Okay, you have to replace it with a terminal eventually. Okay, so that is parse trees. And as we mentioned, it is used to show derivations. So a parse tree has a unique leftmost and rightmost derivation. So we'll see this in the next slide. And a leftmost and rightmost derivation of the same string actually yields the same parse tree. Okay, so um, this is an example. So we have the graph, sorry, not the graph, the CFG here. Okay, so we have a simple CFG, and then this is um, the parse tree of ID times ID plus ID. Okay, so you have ID times ID plus ID. Okay, so we have a unique leftmost and rightmost derivation because from here we have E is replaced by E plus E, and then if we do rightmost, so we replace this E with the E times E. Okay, so so this E gets replaced with E times E here, and then this E, since it's the rightmost, it's replaced by ID, and then this E is replaced by ID as well from here, and then finally the leftmost variable now is E, that's replaced with ID as well. So we get this one. Okay, so it only has one leftmost derivation. And then for the rightmost, we could also have here, so E is replaced with E plus E here. The rightmost is this E, so that's replaced with ID. The rightmost now is this one, so that's replaced with E times E. And then this E is replaced with ID. This E is replaced with ID. So it's also a unique rightmost derivation. But you notice that the leftmost and rightmost derivations have the same parse tree. Okay, so that is how your parse trees are related to your derivations. Now, um, in some grammars, they are actually ambiguous. Okay, and an example of that would be this grammar. Okay, so this grammar is ambiguous because there are two parse trees for this string. Okay, so if we write this one, um, so if we want to yield this string, we could do it two ways, right? So start with S, and S could be replaced with SS, right? But since we have three open close parentheses, I could replace this with SS as well, and then this one would become open close, and then open close. So you have the three parentheses here. But that's not the only way that you could create the parse tree. You could also have from S, you could replace that with SS. But instead of uh, replacing this S with SS, you could replace this with open close, right? And then this S could be replaced with SS, and then this one would be open close, this one would be open close. So you actually have two parse trees of the same string, and that makes this grammar ambiguous. Okay, because you have two different representations or parse trees for one string. Okay, so you have this one and this one. So if you have two different parse trees, that means that there are two different leftmost or rightmost derivations. And if you have two different leftmost or rightmost derivations, that also means that you have two different parse trees. So it's both, it goes both ways. Okay, so so let me show you that they also have two leftmost derivations. So from this string again, the three open close parentheses. So you have from S, it becomes SS, it becomes SSS. Then from here, you could replace this S with open close. So because this is the leftmost, right? So it becomes open close, and then this becomes open close, this becomes open close. But instead of replacing this S with SS, you could have replaced it with open close, and then it would be different. So it only varies in the second step, but that is already a different leftmost derivation, right? The same thing for the rightmost derivation. So instead of replacing this, okay, so instead of replacing this S with SS here, this rightmost derivation replaces S with open close. Okay, and that is their difference. But the rest of the steps look more or less the same, because this S just becomes open close, and then this one becomes that, this one becomes that. So the same lang here. From S becomes SS, tapos right there. Okay, so it looks like they only vary in one step, but in reality, uh, they're already different. Okay, so they have two different leftmost derivations, two different rightmost derivations. So that makes the grammar ambiguous. Okay, so formally, a CFG is ambiguous if there exists a string that can be derived from the CFG and has two or more parse trees, two or more different leftmost derivations, or two or more different rightmost derivations. Okay, so if you have two different parse trees or leftmost rightmost derivations, that means that the grammar is ambiguous. Okay, now take note that ambiguity is a property of your grammars. It's not a property of the language. Okay, what does that mean? Because a context-free language, could have two or more CFGs, right? We discussed that last time, that a language could have multiple CFGs, and some of them could be badly designed. That's why we had to do the simplification. And in the same manner, if you have two or more different CFGs for the same language, one of the CFGs could be ambiguous and the other one could be unambiguous, but they have the same language, right? So ambiguity is a property of the grammar. So it could be because of bad design, or it could be because it was designed that way to be simple, uh, to be simpler, right? So whatever the case may be, ambiguity is a property of the grammars. Now, we don't want ambiguity for our grammars. So ambiguity is bad. So why is that? As an example, let's say that you have the source code, so your program, and then you have the parser, which is a part of the programming language compiler, right? So if you have multiple parse trees for your source code or your program, that means that the parser doesn't know which of the different parse trees should be the right parse tree. So you allow the compiler to pick which among those possible interpretations should be executed, which is wrong, right? Because you want one interpretation of your program and not many different ones. Okay, so when you write your code, you're probably writing it to achieve some result, and you don't want it to you don't want the compiler to make arbitrary decisions on what to do, because the grammar is ambiguous, right? So we don't want that. Okay, now there's also some ambiguity in the English language, right? So some examples of uh, sentences with ambiguity in the language, with ambiguity in it, could be like this. So the lady hit the man with an umbrella. So this could be ambiguous because you could interpret it two ways. So the lady, you could break it like this: the lady hit the man with an umbrella. So there could be a lady here. So there's a lady here, right? So there's and then there's a man here, and the lady hit the man with an umbrella. So she used an umbrella to hit the man. Bam. Okay? So she hit the man with an umbrella. But another interpretation of this one could be um, like this. Could also be the lady hit the man hit or it could be the lady hit the man with an umbrella. So another interpretation could be there's a lady here, right? And there's a man with an umbrella. So the man is carrying the umbrella this time. Okay, and she hit this man. So bam. Okay, so she hit that man. So it's ambiguous, right? So let's see another example. Um, he gave her cat food. Okay, so one interpretation of this one could be he, the guy, gave her cat. So there's a cat here, and this is property of the girl, not property. Probably a wrong property sounds bad. So this is the girl's pet. So this is her cat. So he gave her cat food. Okay, so the cat is now eating the food. But another way to interpret this is he gave her cat food. So this is the guy here. There's a woman here, and he gave her cat food. So this one is cat food. So he is giving cat food to her. He gave her cat food. So that's another way to interpret it, right? So it's also ambiguous. Okay, and last example. Um, okay, the boy saw the girl using binoculars. Okay, so the boy saw the girl using binoculars. Okay, let me change this one. So one interpretation could be the boy is, I don't know, maybe stalking the girl. So he saw the girl using binoculars. So I see her. Okay, but another interpretation is that the boy saw the girl and the girl is using binoculars. Okay, I saw you using binoculars. That's also another interpretation, right? So there's a lot of ambiguous um, sentences in the English language, and those are just some examples, right? But in the English language, we usually use context clues to remove ambiguity in sentences, right? So context clues tells us which is the right interpretation for certain sentences. However, we cannot do that for context-free languages. So because it's context-free, there is no context. Okay? So there's no reference to strings that are external to the language, so you cannot infer the correct meaning immediately. Okay? So whereas we can use context clues in English language, we cannot use them in context-free languages because there is no context in CFLs. Okay? So if that's the case, how do we handle ambiguity? So to handle ambiguity, you could do two things. First, you could write an equivalent unambiguous grammar, or you can just choose to live with ambiguity. Okay, so let's see how to do unambiguous grammar from ambiguous. So let's say that we have this ambiguous grammar here. The equivalent unambiguous grammar could look something like this. Okay, so we will not discuss how to actually like to convert them, but know that for some grammars, it's possible to convert ambiguous to unambiguous. Okay, so the B here represents balanced parenthesis, and the R represents strings with one more closed parenthesis. So because you have an extra closing here, so that's why you need to have a Um, if you have open here, it's closed, and then another close here. So you have one more closed parenthesis. Okay, so that's why in B you have the extra open here, so that if you pair it with R, there's the extra close can be paired with it. Okay. Now, using this unambiguous grammar, you could construct a unique leftmost derivation by scanning the string from left to right. So, for example, you could create like a lookup table. If your current variable is B and the next symbol is open, so from being a open, you will use this one, right? Because B open means that you have to use this production. If it was R and then open, you will use this production, the open RR. If it was B and then end of string, then you'll have epsilon. And then B closed, then you'll use this one. Okay, so you could check the next string and then use that, or sorry, the next symbol, and then use that to decide which production to use. Okay, so let's see an example of that one by deriving this string here using this unambiguous grammar. Okay, so we'll start with the start symbol, which is B. For B, the next symbol is open, so we will have to use this production, right? Because this one also starts with open. Okay. Now, next um, next symbol is the open again, and it is for R. So R on open, we'll have to use this one. Okay, so we'll replace R with this one because we know that the next string is open, or the next symbol is open. So we'll replace it with this one. And then the next symbol is closed, right? And on R, so closed on R has to be this one. So we'll replace it with closed. The next closed on R, so we'll use closed again. And then open on B. Open on B, we'll have to use this one. So we'll replace it with open RB. And then close on R, we'll have to use the close. Okay. And then lastly, B on end of string, so we'll have to use epsilon. So now we have uh, derived the string that we wanted. Okay. And there is no ambiguity because we looked ahead by one symbol to decide which production to use. Okay. So that's it. So this type of grammar is called a LL1 grammar. Okay, so an LL1 grammar is a grammar where you can always figure out the production to use in the leftmost derivation by scanning the given string from left to right and looking only at the next one symbol. Okay, so the term LL1 comes from the leftmost derivation. So earlier we did leftmost derivation, right? And we scan the string from left to right, and we only look ahead by one symbol. So we decide which production to use by checking the next symbol and deciding, okay, so it's this symbol, so I have to use this production. Okay, so that's why it's called LL1. Most programming languages have an LL1 grammar, so that allows them to be unambiguous. And LL1 grammars are never ambiguous, so it's appropriate for programming languages so that you don't have ambiguity in interpreting your source code. Okay, so that's LL1 grammar. Now, unfortunately, some languages have inherent ambiguity. So some CFLs are inherently ambiguous, such that every grammar for that language is ambiguous. So no matter how you try, the grammar will always be ambiguous because it's inherent in the language. Okay, so an example of this would be this language. So 0i, 1j, 2k, wherein I is equal to j or j is equal to k. This is inherently ambiguous. So what is this language? So this is the language wherein you have zeros followed by ones followed by twos, wherein either the number of zeros and ones are equal, so you have I is equal to j, or the number of ones and twos are equal. Okay, so you could have things like um, you could have things like um, 0, 0, 1, 1, 2. So you have, this is okay because you have equal number of zeros and ones. You could have 0, 1, 2, 2, 2. So this is also okay because you have an equal number of zeros and ones. You could have things like 0, 0, 0, 1, 2. This is also okay because you have equal number of ones and twos. Okay, or 0, 1, 1, 1, 2, 2, 2. So this is also okay because you have equal number of ones and twos. Okay, so those are some example strings. Um, But this is inherently ambiguous because some strings of the form 0n, 1, and 2n will be generated by two parse trees. So one would be based on checking the zeros and ones, the other would be based on checking ones and twos. Because you have or, right? So either I is equal to j or j is equal to k. So it doesn't really matter. So um, the ambiguous grammar for this language would have to be something like this. So it's either AB or CD, wherein AB here means that you have an um, AB, that means that you have equal number of zeros and ones, because you have 0, 1 here, so you have equal number, or if you have a 0 here, you must always pair it with a 1, and then you have A in between, so that you can have, if it's 0, 0, 1, 1, that would be from AB, A would be, or not if it's B. So if it's just for A, right? So you could have 0 A 1, and then this would be 0 1. So you have 0 0 1 1. 0 0 1 1. Yeah. Okay. So you have zeros and ones, and then for B, you could have any number of twos, right? Because you have 2, 2B, and so on. So you could have any number of twos as you want. And then for CD, it's the opposite. So you could have any number of zeros. So you have 0C or 0 here, so that you could add as many zeros as you want. Or 1D2, 1, 2. So the number of ones is equal to the number of twos. Because you could have 1, 2, so you have an equal number of 1 and 2. Or if you have D in between, so that means that you could nest them inside. You always have 1 and it's paired with 2 here. Okay? So A means you have an equal number of zeros and ones. B has any number of twos. C is any number of zeros, and D is equal ones and twos, as we said here. Okay. So strings of the form 0n, 1n, and 2n will have two derivations. For example, 0, 1, 2. Why is that? Because for S, we could have AB, and then from AB, this will be replaced with A will be replaced with 0, 1, and then B will be replaced with 2, right? So that's it. And then you could also have S could be equal to CD, wherein C will be replaced with 0 and D will be replaced with 1, 2, right? So you have two different leftmost derivations, okay? So this one is inherently ambiguous. Unfortunately, there is no known algorithm to convert ambiguous grammars to unambiguous grammars automatically. You have to design it yourself, okay? So in that case, what should we do if we cannot convert it to an unambiguous grammar? So the other option is you could just live with ambiguity. Okay, so if you have an ambiguous grammar, it allows it to be simple, because earlier you noticed that from a simple grammar we made it convoluted or complicated by making it unambiguous, Okay, so that's the um, drawback, or that's the downside of having an unambiguous grammar, is that it's not simple anymore. Okay, similar to how we did automatas in the past, like finite automata. If it's NFA, where you have ambiguity, so you don't know which path it will choose, the design could be simple. But if you convert it to a DFA where it's deterministic, it could become bigger and complicated. So it's the same with CFGs. So if you have an ambiguous grammar, it allows the design to be simple. But if you have an unambiguous grammar, it becomes a little bit more complicated. Okay. Having ambiguous grammars also allows more natural definitions, like next nested structures. Okay. So how do we live with ambiguity? Most parsing tools allow ambiguous grammars, provided that you have a disambiguation mechanism, or a way to disambiguate, or break the ambiguity. Okay, so this a disambiguation mechanism is a way to tell which parse tree we want. Because if you have ambiguity, remember that you would have multiple parse trees as a result, right? So the disambiguation mechanism will tell the parser, hey, I want this interpretation. Okay, so use this one. So that is a disambiguation mechanism. So examples of disambiguation mechanisms are precedence and associativity. So you're probably familiar with these terms from your ComSci 124 sa in your oh, are you taking 124 right now? I'm not sure. Basta in your programming languages the class. Okay. So for example, if you have this grammar is ambiguous because it has two parse trees for the string id times id plus id. So just quickly, let's show that as an example. Um, how it has two parse trees. So from E here, we could choose, uh, well, first we could choose E times E, right? E times E. And then since this is multiplication, the other side is plus, so this becomes E plus E. Then the rest of the E's could be replaced with ID, right? So this will become ID, ID, ID. So that is ID times ID plus ID. This is one. Another parse tree would have been E is equal to E plus E, right? Okay, so I'm taking this plus this. And then I'll replace this E with E times E. Then I'll replace this with ID, ID, ID. So that's also ID times ID plus ID. So those are two different parse trees. So it's ambiguous, right? Okay. So um, a disambiguation mechanism could be precedence. So for example, multiplication in most programming languages binds tighter or has higher precedence than addition. So that ID times ID plus ID should be interpreted as ID times ID first before adding it to this one. It's not, you don't add first before multiplying, right? So that's precedence. So it tells you that you have to do multiplication first before addition. Okay, so this is for different operations, precedence. Associativity naman is for similar operations. So if you have multiple plus operations, how do we interpret it? Okay, so plus and multiplication are both left associative operators. And what that means is that if you have A plus B plus C, so this is all multiplication. So how do you interpret that? Because you could have a parse tree that looks like, um, could be E plus E, then so this could be A, E plus E here again, B plus C. Or is that E plus E, E plus E, A, B, C? Is that this one or this one? So for A plus B plus C, since plus is a left associative operator, we group it from the left. So A plus B first before adding it to C. Okay? So if it's A times B times C naman, we group it here first before this one. So the correct interpretation is this parse tree, not this one. Okay? So on the other hand, there is also some operators that are right associative. And an example of that is equals. So for example, A is equal to B is equal to C is equal to D should be interpreted as C is equal to D first, and then whatever the value is here, B is equal to this one, and then A is equal to that one. So it's right associative. It should not be A is equal to B first and then equal to C equal to D. It's not this one. So it's right associative. Okay, so that is associativity. How to handle operations of the same kind. So is it left associative or right associative? Whereas precedence naman is how you handle different operations. So which comes first? Multiplication or addition? So you have the PEMDAS usually for that one. Okay, now why do we care if ambiguous if grammars are ambiguous or not? So if you have an ambiguous grammar, some strings in the language have different parse trees, as we said. And if you have two different parse trees of the same string, like for example, if your string is the source code, that means that it will have two different meanings. Or in case of your source code, it will have two different programs, right? Two different interpretations. We don't want that because, of course, we want our code to do exactly what we want it to do, not do something else, right? So if you have an inherently ambiguous language, those are not suitable as programming languages because we don't want our programming language to decide if there's ambiguity. Okay? There is no way of fixing a unique structure for all its programs because it is ambiguous. So, um, okay, so we don't want ambiguity. And the reason why we want to do this is because this is important in the compiler phase, right? So you'll learn more about this in detail in your ComSci 124 programming languages, but the first two steps in compiler uh, in the compiler processing is first you have the lexical analysis. So the lexical analysis converts the strings into a list of tokens. So let's say you have your source code. Let's say your source code looks like this. If so let's say x is equal to 5. If x is equal to 5, print high, something like that. So let's say this is your source code. So the lexical analysis part will convert this whole string, your source code, into a list of tokens. So how will that happen? You will use regular expressions for this one. So for example, it will break variables, and then the equal sign would be 1, and then literal ints, and then another keyword here is if, then you have a variable again, then you have a equal operator, and then you have another literal, and then a colon, uh, colons, yeah, a colon that opens the block. Then you have the print statement or function, you have the open parenthesis, you have a string here, and then the close parenthesis. So it breaks your string into a list of tokens, and you use regular expression for that one. So these are just patterns, right? So remember this from last time. And then the next step is parsing. So you, given this list of tokens, you produce the parse tree and check whether the parse string follows the correct grammar. So our programming language uses a CFG to represent the grammar of the language, and that tells you the correct syntax. So for example, for this one, it has the correct syntax, so this should form a correct um, parse tree. But for example, if what we did here was something like um, something like x equals plus 5. So we don't have this one, right? So because we don't have equals plus, we have plus equals. So that would be interpreted as equals and then a plus here. So that would be broken as two different tokens. And then it will not be interpreted correctly by the parse tree. So it will yield an error. So that is why, or this is when your compiler yields a syntax error. And that tells you that your code does not follow the correct syntax or the correct grammar. Okay, and we use CFGs to check that one. Okay, so in parsing, we have several parsing algorithms. Some of them are CYK, Early's method, shunting yard. Then you usually have the more generic top-down and bottom-up parsing. So for this lecture, we'll just discuss the top-down and bottom-up, just to give you an idea of how some parsing algorithms work. Okay, so first, you have the top-down parsing, or also known as the recursive descent parsing. Um, And what this does is you construct the parse tree from the top, from left to right, and then you go down. Okay, so that's why it's top down. So what you do is you start with the start symbol and you try the rules for the start symbol in order. So you check them one by one, and it could involve backtracking if we can't find the correct solution. Okay, so you try to replace it with one of the productions. If it works, continue. If it doesn't, look at the other production, and if you've tried other all the possibilities, go back up and change a previous step. So that is backtracking. Okay, so for example, if this is your uh, grammar, and you're trying to um, derive this string, so you start with E, and then you start with this one, so E becomes T, and then from T could become int, but it doesn't fit here, right? So we won't do that. We'll try int times t, but that also won't fit here, so we won't also do that. How about t becomes e? Okay, so maybe we'll continue with this one. So we'll replace e with t, and then t again will be replaced with int, and now we have derived this string because that is now open int close. Right? So that is how you do top down. You start with start symbol, replace it with one of the productions in order, and then if it fails, go to the next one. If it fails, go to the next one. If it has failed again, you have to go back here and change it. Okay, so for example, what if it was um, int plus int? What if we were trying to derive this one? So if it was int plus int, that would be e and then t, and then t would be replaced with int, but that will not fit. T replaced with int times t, that's also wrong. With parentheses, then t and then int, that will also be wrong. So since we have tried all possibilities for t, that means that maybe t was the wrong choice in the first place. So we'll replace that one and go back here sa e. So since this one is already wrong, we'll try the next one, which is t plus e. Okay, so from here, okay, so let me rewrite that here. If e is t plus e, this could be int, then e could be t again, and then t could be int. And that is now the correct parse tree. So int plus int. Okay, so that is how you do top-down um, parsing. So yeah, this was the example earlier. So for top-down parsing, the most common top-down parsers are LLK parsers, where K is a number. So an example of that is the LL1 parser that we saw earlier, right? So leftmost derivation, left to right scan, look ahead by one symbol. So, however, top-down parsing has a problem, which is the left recursion, and it could lead to infinite recursion. So, what is left recursion? Um, there are some direct left recursions like this. So, what that means is that if you have grammars of this form, A is equal to A plus B. So, what will happen is that A will be replaced with A plus B. But because you're doing leftmost derivation, this A again will be replaced with A plus B, right? And then this A will be replaced with A plus B again, and so on. So that's why it's called left recursion, because you're just doing recursion on the left side and it will not end. It's infinite, okay? There could also be uh, indirect recursions. Like this one is pretty obvious because you have A here and then it's replaced with A on the left side. So since you're doing left derivation, you'll always replace it here. But there could also be indirect left recursions like this. So A to BAA, like that, and then from B it's replaced with AB. So it doesn't look like it's doing recursion yet, but from A again you'll go back to BAA, and then from B again you're going back to AB, then and so on. So this part here is recurring here again. Okay, so that is indirect left recursion. So that is a problem with your LLK grammars. But there is an algorithm to remove direct and indirect left recursion. Of course, we won't discuss it, but there is a way, okay, to remove this. So it shouldn't be a problem. But just be aware because some grammars have this problem. Okay. Now, the other type of main type of parsing algorithm is called bottom-up parsing. So it's the opposite naman. So you start by construct the derivation by starting with a given string and attempting to find immediately previous sentential forms. So sa top down, you started with the start symbol and tried to derive the string. But in bottom up, you start with the string and try to derive all the way to the top ang start symbol. Okay, so it's the opposite direction. So it's also known as the shift reduce algorithm because you shift or you push the next input token to the stack and you reduce by replacing a right hand side on top of the parser stack by its corresponding left hand side. So you're trying to reduce it into the start symbol eventually. Okay, so let's see an example. Let's say we want to derive the same string, the int, and then using the same um, grammar. So we start with int here. Okay, so from int, so int is here, right? So what could we replace this with? So since int siya, could be replaced with t, right? So this int could have been t. So that would have been open t close. Now this t could have been e here, right? So if we replace t with e, that could have been open e close. Now if this was open e close, this whole thing right here could have been t again. So we can replace that with t. And then again, this t could be replaced with e. And so we have derived the start symbol, which is e, and now we are done. Okay, so that is bottom up. You start with the string, you try to replace some of um, the terminals with variables, and then productions. So you could replace the whole thing with another variable until you reach the start symbol. So that is your goal. So from int to t to e, t. Okay, that is bottom up parsing. So in bottom up parsing, the most common ones are known as LR parsers, wherein you do left to right scan, but you're doing rightmost derivation. Okay, so it's not LLK anymore, so it's LR. So rightmost derivation naman. So example of this would be the LR0 parser in some cases. Okay, that's bottom-up parsing. Now, if you've watched the Silicon Valley na series, there was also something they mentioned called the middle out, and actually, uh, some people are actually using this one also, right? So top down, bottom up, and then middle out. But that's for those who have watched Silicon Valley. Anyway, so that's it. That's it for this video. So to review, we discussed parse trees, which is a way for you to show your derivation, right? So it's a tree that has terminals and variables in the nodes. It shows you the leftmost and rightmost derivation, and also shows you ambiguity, right? Because grammar is ambiguous if you have two different parse trees. We also discussed how to handle ambiguity. So number one, you could write a equivalent unambiguous grammar, or you could just live with the ambiguity. But you have to provide disambiguation mechanisms like precedence and associativity. And then we also discussed the difference between top-down and bottom-up parsing, wherein from top-down, you start with the start symbol and try to derive the string going down, whereas in bottom-up, you start with the string itself and try to replace it with previous intentional forms, and your goal is to eventually find the start symbol. Okay, so that's it for this video. The next topics would be push-down automata and equivalence of push-down automata and CFG. So we have already discussed the structural representation for CFLs, which is the grammar, CFG, context-free grammars. The next discussion would be about the automata, which is the equivalent automata for your context-free languages. Okay, so that's it for this video, and I will see you next time.